Okay. So streaming is on. So are there any questions about the family or cousins homework assignment? I just thought, you guys might need to know one more thing, which is equality check. How do you compare two things and, see whether they are the same or not? So that's one thing you can kind of do a research on your own and actually try to figure that out. But I'm going to tell you anyway, just so that, you it makes it kind of easier on you guys. All right, so we'll go ahead and take a look at, um, okay, we'll just make a test Prolog program here. And I'll just make this not equal to, right? So not equal to xy and not equal to xy if and only if it is not the case that x equals y. That's it. So the backslash plus is the negation, not, and then x equals y returns true if and only if x and y are the same. Okay, so are we good with this? So let's go ahead and test it, okay, because we want to make sure that this does work. So we'll go to SWI prolog, read the file in. I'm not sure whether it can do a different path. We'll give it a test. And it does not like that. It does not do the slash. All right, fine. We go to the folder and then do the SWI prolog here. And it's test and then a period. There we go. So we say not equal to, we can give it two things that are the same, like, x and x here. And it says it's false, okay, which is true, because if they're the same, then they are not equal to. X is not equal to x. Okay, x and y are different, so they return true. So that means this mechanism does work. So the reason I kind of want to mention this is, you need this in order to make sure that your program works, in order for your program not to identify siblings as cousins. Okay, because the only difference between a sibling and a cousin is, their parents are different. Yep. But you must have a common grandparent in the case of a first cousin. So are we doing okay so far? Good. Okay. And when you need to do the relationship recursively, you have to use the is operator, so that you can come up with a new variable that is one less than one of the variables of the current clause. So you need to use is. That idea was demonstrated when we talked about the factorial program. So if you want to go back to the factorial program, you can see how we can do recursion, where one number gets smaller, when it does the recursion. Are we doing okay so far with that? Okay. Yep. Okay, so let's go back to the factorial program. I believe so. Yep. So there's a red dot here. It should be streaming already. So when you look at the factorial program as a tutorial, this is how it's done. So the key part here is the word is. It's basically assignment, which basically means n has to be greater than 0 and n1 is n minus 1. But instead of trying to instantiate every single integer into the spot of n1 to see which one is in fact n minus 1, it just computes n minus 1 and then store it into n1. So the is kind of like the assignment operator in C and C++, and the direction is the same, which means n minus 1 is computed first, and then n1 gets its value. Yes? Does similar do like an assignment or comparison? It does a comparison, but it does a numerical comparison and only a numerical comparison. So if you want to compare atoms, you need a double equal. It also has a structural comparison, which can compare two lists, and lists in Prolog can nest. So there's one that actually structurally, recursively check whether two things are structurally the same, which is kind of cool, but we don't need that, for this assignment. So are we doing okay so far with this? So if you have not gotten started with this or it's not working yet, I would recommend that you do it in a simpler way. Define a very small family tree where it is easy to check whether one particular atom should be classified as a cousin of another atom. And then the other way to do it is to also to specify XY0 is just define that as siblings. Okay, is that okay? So let me just kind of write it down here, and so it's recorded. Because your recursion has to stop at some point. And the idea for your recursion to stop here, well, it's not, okay, fine. I'm going to use VI. Okay, so what you want to define is cousin, CL cousin, and then you have X, Y, and then 0. And somehow define this side to basically say if X and Y are siblings, then it returns true. Is that okay? I'm not going to tell you how to do it because that's actually pretty simple given that we already have parent of relationship amongst the atoms. So you want to define this first. This is the non-recursive version of cousin, and then you can define all the other cousins recursively. Because you can define the second cousin using first cousins. You can define the third cousin using second cousins, and so on. So that's something you might want to think about, is how do we define cousins recursively. If you read online, okay, you might actually find hints of how to do that stuff already. You might, okay, so I'm gonna, let me look up third cousin, for instance. So if you look up third cousins, the definition is the child of one's parent's second cousin. Do you see how it's recursive? There you go. So you have to pick two individuals where their parents are second cousins. Is that okay? So you can define, cousin XY0 as siblings because your first cousin is the normal cousin. That's how we usually refer to cousins as. So all the other cousins can now be defined recursively. All right, are we kind of doing okay so far here? Okay, cool. All right, so if this is all okay, the next thing I'm going to do is to give you guys a practice exam. That's what that's what I said we would do today. And then I'm going to hide this a little bit here so I can go find my exams. Not that, it's really a big secret, but I still want to kind of put it on the side. Because I want to give you the most updated one, which is 18 fall. And there's no way I can actually accidentally give you the one for this year because it has not been made yet. So let's see. Oh, right. So I need to look for 189 fx. Okay, that works. All right. So this is one version of that test. There are many versions. There we go. All right, so this is the exact exam, of fall 2018. So really, it's just from the last semester. Most of this stuff is relevant, but the classroom obviously and the time would be different. So do you guys remember when our final exam is? It's 1 week from today, starting at 12:45. That's right. Okay, so that's good because the exam time is a little bit later than the usual time. So if you just, it's just a force of habit and you have to show up at noon, you'll just be like 45 minutes early instead of being late. So that's all good. All right. Open material, meaning anything that is printed or handwritten prior to the exam, um, you can bring it here. This actually does not apply. I forgot to change the text. So unless someone is taking the exam late, they cannot get an exam from earlier. Okay, by any means. So I would assume that people do not possess any knowledge of the questions when they take this test. Um, so this part here is just the usual stuff. Work individually. And so on. Okay, so nothing really new. I mean, all of this stuff is in your second and the first exam as well. You might want to bring additional pieces of paper if you think you will need those. And if you do that, and if paper is not too expensive, you might want to just write down your name before the test on those extra pieces of paper. So if you think I might need 3 pieces of paper, just bring those and then pre-write your name on those paper, just so that you don't forget and it doesn't use up any time during the exam. Make your answers as complete as possible. Okay, so you want to explain the steps of your reasoning, because that is what I'm going to use for grading, is your reasoning. If you don't show me how you come up with the answer, you cannot get full credit, because I need to know how you came up with the actual answer. It doesn't have to be in mathematical symbols. It can be like sentences, it can be incomplete sentences, and so on. But I need to know, how you process the question, how you think about it, and how you solve the problem. Some questions may cross pages. Be sure to read and answer the entire question. And this part here obviously also does not apply. Your final exam is only going to account for 40% of your grade and not 53%. Last semester we got the smoke issue. So, second exam did not happen because, the school was shut down for what, a week and a half or something like that. And that was exactly the time when I wanted to have exam 2 to happen. And so, so it was kind of brutal because, the final exam is now more than 1/2 of the grade of the class. Yep. All right, so that's just the usual stuff, nothing new. So question number 1 of 5. So certain questions, I use this kind of double column, kind of format to save space. So this one is using the A-star algorithm, and the A-star algorithm is provided here. So whatever algorithm you'll be tested on, I will provide the algorithm, even though it may be identical to the one in the textbook, but it will be kind of like a shorter version of it, so you don't have to read all the explanation and whatnot. So this is the A-star algorithm, kind of compacted a little bit. And the first question, okay, where is the first question? Okay, there you go. So the first question is, first determine your own heuristic function so that the algorithm does not even put vertex u into the set O during the execution of the algorithm. So this part, goes back to, the way the A-star algorithm, and I want you to design or hand, cater, the H values so that vertex U does not get put into the set O at all for the entire duration of running this algorithm. The start vertex and the end vertex are already given to you. So let's see, am I missing anything back here? Okay, so the destination vertex is Z. Oh, the start vertex is S. Vertex M. Okay, vertex M is the start. So this is our start vertex. And then vertex Z is the end vertex. So this is the start, this is the end. And we want to avoid putting vertex U into the set completely. So I want this vertex not to be put into the set O. So you have to come up with the H values so that that happens. So how do we get started with this? Okay. Well, the first thing is you do have to find the shortest path, or at least find the length of the shortest path from each vertex, because you have to make sure that your heuristics are not overestimating. Okay, so that's pretty easy. The shortest path from R to Z is just 2. The shortest path from U to Z is 9, as far as I can tell. Yep. Hmm? It is the only path. Yep. And then the shortest path from P to Z. Okay, so P has several paths to Z. This one has 7. This one has 9. 7 is the shortest one. And then M has, once again, several paths. There's an actual loop here, which is kind of cool, because you can see the loop involves 2 edges that have 0 cost. So M can go through here, which means it has a path of 8 units, or you can go through this, which is longer. So this is the shortest one. Huh? U does not get to Z directly. U goes to R only. But it does come, you can go to U from Q. You can also go to U from Z. Okay? All right. So now you have to set up the heuristics so that U does not get explored. It does not get put into the set O. Now, when do we put something into O, the set? Because that's basically what the question is asking, is can you analyze the code, find out the line that puts a particular vertex into the set O, and then you ask, how do we prevent that from happening? So, say again? Can you speak a little louder? Okay. All right. So there are only 2 lines that can put something into O. And okay, I think I can use a pen this time. Okay, there are 2 lines that put something into O. The first one is the initialization, which is not something that is of great concern to us. So line 9 is one line that puts something into O. It only puts the start vertex, which in this case is vertex M, into the set O. So it's not a big deal, okay? There's only one more line that can put something into the set O, and which line is that on? Line 16, that is correct. Okay, so it's line 16, huh? Line 12 only removes something. It does not put something into O. It only removes the vertex that we have chosen on line 11. So the set gets smaller, one element smaller than before. Okay, so line 12 is not a concern to us. It is line 16 that is a concern. We do not want line 16 to put vertex U into O. Okay, so vertex U will be our variable n here. And then the way that we get n is for each thing here, where C is chosen earlier, and then we have an edge from C to n, and then if n is getting a shorter path, then we put it into O, the set O. So now you have to go kind of walk backwards a little bit. So you have to basically say, we need to make sure that this condition on line 15, this condition, does not get true. Well, it's pretty hard for this not to be true if n is in fact vertex U, because that means we have just found a path, okay, from the start vertex to vertex U, as opposed to we did not know of any path from the start vertex to vertex U. Because remember, how did we initialize all of the G values, like G of U? How do we initialize those? I mean, it's in the code here. They're all initialized to infinity, except for the start vertex, right? Well, U is not a start vertex, so it's definitely initialized to infinity, which means if I do find a path from the start vertex to vertex U, it's going to get to this code here. And this condition on line 15 is going to be true. So we have to make sure that whoever is leading to U is not, going to put itself into the set, or if it does put itself into the set, it will never be extracted out of the set. Is that okay? So it's not just vertex u that we are concerned about. It is whatever vertex that can lead to vertex u. Yes?
So, like, do you mean we just need to pick a heuristic for the thing before you to be too high?
Yes,
And is that going to make line 11 never pick the thing before you?
exactly. So we leave it out all the time.
Okay.
So what we need to do then, okay, so if you look at the graph here, we basically want to make sure that,
It never goes to Q.
hmm?
It never goes to Q, the heuristic for Q.
Well, there are two vertices here. The destination is not the issue. Okay,
Right.
so the other only issue is Q.
Right.
So we have to make sure that um, the heuristic from U to Z has to be as high as possible.
Not Q. From Q to Z.
Wait,
From Q to Z, right. From Q to Z, it has to be as high as possible. So that will make Q look very unattractive, when we try to pick the next vertex to explore from O. So now we have to basically say, make sure that looks super unrealistic, or not unrealistic, but as realistic as possible, which means it is the actual path, length of the path.
And
Say that one more time.
you said 10.
So it is 172, so it's 10. So we want the heuristic value of Q to Z to be 10. Okay? So now that this is decided, do we need any other special consideration?
I don't think so.
Well, because it is not on the shortest path. If it is actually on the shortest path, we cannot stop. If U is actually on the shortest path, we cannot stop the algorithm from expanding to it. Okay, but since it's not, we just have to make Q looking as unattractive as possible, and then the rest can all be zeros.
Sure. That's good.
Yep,
But so the heuristic can't be over the length of the shortest path from Q to Z?
correct.
Isn't the shortest path from Q to M and then P to R, R to Z?
From Q to Z is
To the left?
172.
No, he means going the other way.
Oh yeah, yeah. You can go the other way too. You can go 0, 1, 5, 2. So 8 is correct. So it's actually 8. Yep, you're right. Yep, good point. So make that as realistic as possible, and then it won't get explored. So then
If you so if you violate that, the admissible heuristic in this case, will it still find the shortest path?
if you violate what again?
Like if we did pick 10, it wouldn't be admissible anymore, but would it still find
It
the
was
shortest path?
in this case yes, because the vertices on the actual shortest path, as long as they still have they still meet the requirement of not overestimating, you'll still be okay. Because what you're overestimating is the heuristic of a vertex that is not on the shortest path from M to Z. Yep. But generally speaking, we want to keep our heuristics, not overestimating. So are we still doing okay so far with this? So now the next question, or the next part of the question, now that you have selected the heuristic values, so the rest can all be zeros. They don't really have to be anything else. Then you want to trace the algorithm in the provided sheet. So the provided sheet is either the following page. Yep, in this case it's just the following page. So now we have to kind of track, the execution of the algorithm in this sheet here. And then you have to basically, when I look through this sheet, I will be looking at, do you understand, how the algorithm works? Okay, are you updating the GF and the previous values at the right time? Are you selecting the correct element from O to become variable C? So those would be the kind of things that I'll be looking for as I go through this particular sheet. Yes.
Will you be providing these sheets?
Yes. So I'll be doing the same thing or very similar with the final exam that you guys are going to take.
This is not on Canvas, so you won't.
This is not currently on Canvas, so I'm gonna have to put it up on Canvas.
Thank you.
Mm-hmm. Yep.
Would the algorithm that's given on the textbook be similar to one on the textbook, or is it going to be different?
It's gonna be very similar, but it may contain minor differences. So you still want to be careful, like, just follow the algorithm and not assume it is the same. So are we still doing okay so far with this one? Do we know how to trace this? Okay. So this would not take you too much time, because I tend to give you guys like simpler, graphs. Even though it looks nasty with loops and whatnot, we know that both Dijkstra's algorithm and A star, they don't really, they don't get tricked by loops. So are we okay with question number 1? Okay. So once I post this, you guys can work on it, and then we still have Wednesday to talk about it if you want to talk about it on Wednesday. Okay, this is question number 2 of 5, and this one is this was second in the second. This is in our second exam, so I'm not gonna put it in the final exam for this class. But we have prologue, and we got complexity stuff. So it's question number 3 of 5, and this was also in our second exam, so I'm not gonna put this in the final exam. You can, because last year they did not get a second exam. That's why you can see all the things in your second exam is on their final exam. Here's the next one. Oh, question 4. Okay, now we are back to A star. So refer to the A star algorithm in listing 1, line 10 is a little more optimized compared to the other published A star algorithm. So this is where it is important to use the algorithm that I list, because it may or may not be the same as what you know of as the A star algorithm. Specifically, the second condition of the conjunction is missing from many A star algorithms. So this is the condition that is missing. There exists at least one vertex v in O such that f of v is less than g of x, x being the destination vertex. Okay. All right. So now the question says, okay, TAC theorizes that this additional condition does not prevent the A star algorithm from finding the shortest path. Use proof by contradiction to show that TAC is correct in the assumption of the heuristic does not, assuming the heuristic does not overestimate. Or if you think TAC is probably wrong, then you can find a counterexample where, if you follow TAC's algorithm, then this graph, the algorithm will not find the shortest path in this particular case. So you can do either one, okay? But one is the correct answer and the other one is probably not. So now the question is, how do you get started with this one? So you have to look up all the keywords, right? So what are the keywords of this question? Proof by contradiction. All right. So the keyword is proof by contradiction. So once you know it is proof by contradiction, this is the keyword, then what is the next thing you need to look for? What is the theorem? Exactly. So what is the theorem that we want to prove by contradiction? What do you think is the theorem? There's a word that is pretty close to theorem that suggests whatever follows is most likely the theorem, right? So this additional condition does not prevent the A star algorithm from finding the shortest path is the theorem, okay? So the theorem is going to be this part here. Okay, now since we're trying to prove by contradiction, what do you need to do next, now that you know it is proof by contradiction and what the theorem is? You negate the theorem. So what happens when you negate the theorem? What is the statement, after you negate it, this theorem itself? So there's at least one case, right? There's at least one case where this additional condition prevents the A star algorithm from finding the shortest path. Now you have to show how that is not possible. Okay? So how do you show that is not possible? In other words, this condition is false. Okay? This condition is, let me think about it. So the algorithm contains this as in part of the conjunction. So that means this condition has to be true to stay in the loop, which means if this condition becomes false, the loop is going to end early, right? So if the contradiction, if the negated theorem is true, that means sometimes we got out too early when we have not found the shortest path. That's so you have to show me why that is not possible. Is that okay? Hmm? Say that one more time. How do we do that? Okay. So now we have to go back to the algorithm. So we have to go back to the algorithm and then identify what is the key part that we are trying. What is the point that we want to make? So we are basically saying that this portion here is if this is false and there is a shortest path that we have not explored, that is not possible. Okay? But we are also making the assumption that the heuristics are not overestimating. So we're playing by the same rules. We're just saying that this condition is now using the negated theorem. We're saying that this is messing things up. Okay? We're exiting the loop too early, and we end up not finding the shortest path. Is that okay? All right? So now we have to ask a question. What does it mean when this condition is false? Okay. So let me, huh? Well, let's find out. Okay, let's just work on the Boolean algebra part and say, okay, what does it mean when we say it is not true that there exists V in O such that f of V is less than G of X? Okay, so we are looking at the negation of this entire thing. So as usual, what we want to do is to push the negation symbol all the way into the inside, because that makes it easier to read. Then we know what it means, right? So the way to do this is to say this is the same thing as saying the same thing as for all V in O. It is not the case that f of V is less than G of X. Okay? And then you can simplify that one more time so it looks nicer, because not less than is the same thing as greater than or equal to. Okay? So we'll say it's the same thing as saying f of V is greater than or equal to G of X. So now we look at this and go like, so what is so significant about this? What do you think? So now you have to remember what is f and what is g. Okay, what is f of v and what is g of x? What are they representing? Okay, say that one more time. That would be g. Yep. F is the one that incorporates the heuristic on top of knowing how much to get there. So let me just repeat that one more time. G of x is the actual length of path from the start vertex to the destination vertex. Okay, that's something that we know we have confirmed already. F of v, on the other hand, is the estimated length of a path from the start vertex through vertex v to the destination. Are we doing okay so far with that? Yes? Okay. So if every single vertex in O, okay, has this particular property, why can I claim that there are no more shortest paths? Or if I say that there's one shortest path still existing here, then we have a contradiction. Right, so if there is a shorter path, right? If there's a shorter path, then g of x is not the shortest yet, right? But f of v is all the v's, for all the v's, your f of v is already greater than or equal to g of x, and the new one is supposed to be less than that. Is that okay? So now you think about, okay, why is that not possible? Because each f of v is g of v plus the heuristic from v to x. Is that okay? All right. And we also know that the heuristic values are, they're one positive and two, they're non-negative, they can be zero. They're not overestimating. In other words, when you look at f of v, it's kind of giving you an idea of this is the best we can do. Okay? We cannot do better than that. So if this is claiming, if this is true, for every v in O, this is already true, that means for every vertex in O, okay, you cannot find a shorter path through any one of those vertices from the start to the end. Is that okay? So that's kind of the explanation that I want you guys to present in a proof like that. Yep.
I want to make sure I understand like why we set it up this way. So the theorem is that if we do take it out, nothing will be wrong. So we're assuming that if we don't take it out and something were wrong, we would get a contradiction. That's why we're doing it like this?
Correct.
Okay.
Yep. So you're basically saying, okay, this condition is false, which means the original condition is false, which means the negated version is true. So we are saying that this condition here is true, and there is a shorter path to vertex x, and then you try to explain why that would create a contradiction. Is that okay? So we're good? So when I'm grading this, I'll be looking for a few things. I'll be looking for, did you set up the proof correctly? Did you identify that this is proof by contradiction and this is the original theorem? Did you understand that in a proof by contradiction, you have to negate the theorem first? So I look for the negative theorem. I look for the interpretation of the negated theorem, okay, something like this would be good, or something that is an explanation of what that really means is also just as good. Then I look for some derivation, okay, you have the negated theorem, and I look for the derivation or explanation. It doesn't have to be all in symbols, and then you come to a contradiction. And then I'm looking for the final part of your proof, which is, since there is a contradiction, the original theorem is in fact true. So I'm looking for all of those steps. Yep.
I don't think I get why the very last for all statement there means that like why it contradicts anything. Can you explain that?
Okay. So what we are now saying that this is true. Okay. This is the negated theorem, but we are also saying that there exists a shorter path to x, right?
Yeah.
So if there is a shorter path to x, but this condition is also true, then so your shorter path has to go through some vertex, and those vertices, they have to be, it has to go through one of the vertices in O. Okay, so does that part make sense?
So do you mean that we're talking about like at the end of execution? So like
Nope, this is during the execution.
Okay.
This is during the execution. At some point of the execution, this condition becomes true, which means this condition is false, so we're getting out. But there is still a shorter path that we have not found yet. And now we have to find out why that is causing a contradiction.
I don't get it. I don't get it.
You're not connecting the,
Yeah, I don't see the connection.
you don't see the connection.
So like what about that statement
Hmm?
contradicts there being a shorter path? Right? That's the part where I'm getting lost.
Okay, the first thing is, can we agree that if there is a shorter path to x, it is going through one of the vertices in O?
Yeah.
Okay, so now the next question is, can we agree that each f of v is an underestimate of the length of a path from the start vertex through v to the destination vertex? Is that okay? All right. So that means now we have a contradiction because let me actually write this out. Okay. Because if I say there exists a shorter path from the start vertex S via vertex, I'll call it W, okay, to X, and W is an element of O, okay, that implies G of W. Now G of W is representing the length of a path from the start vertex to W at this point, okay, plus H of Wx, which is the heuristic, which is an estimate, which can only be cannot overestimate. Okay, so that means this has to be less than g of x, because we said that not what we found is not the shortest. This is shorter, right? But this is now directly, because when you look at this, what is this value? This is how we define f of w. So now we are saying both things, right? We're saying there exists one w in O such that f of w is less than g of x, and we are also saying that everything in O has a f value that is greater than or equal to g of x. So now that is a direct contradiction.
So we're saying that the condition in the while loop is false, right? So the while loop exits. So wouldn't we be at the end of execution at that point? Or about to be at the end because we'd stop like
Yes. Yes.
So the argument's just that at the end of execution, there's a conflict between our estimate and actual values, and like it not having the shortest path, or there being a shorter path.
Correct. Because the only way for the program not to find the shortest path is due to this is for it to exit too early before the actual shortest path was explored.
Okay.
Yep. So are we doing okay so far with this? Can we see the direct contradiction here, and also the assumption that the shortest path is going through one of the vertices in O. Okay. So are we good with this question, number 4? Okay. All right, so let's move on to question number 5. This is 4, and this is question number 5. So question number 5 is also referring back to the algorithm. The A-star algorithm can revisit edges if the heuristic values are non-negative and do not overestimate, and that the distance of edges are also non-negative. Show a graph. Give me an example. Define the start and destination vertices. Define the distance of the edges, so the function d. Define the heuristic values so that the A-star algorithm will revisit at least one edge. This means the same edge is considered more than once in the execution of the A-star. Okay, this is typo, not the. Okay, of the A-star algorithm on line 13 of listing 1. While you can come up with your own graph, this is a simple one that works. So you just have to use this graph and find out what distances and what heuristic you should use in order to create that condition. Yes?
Give us a graph?
Huh?
Are you going to give us a graph?
You mean for this semester?
Yeah. If you give us a questions like this.
It may or may not. I am known to ask questions in entirely different ways between semesters. And Will has probably backtracked how many years of my tests. So it depends on the complexity. If it's something I think, okay, you may not, know, what structure of the graph, will give you the answer. I might give you, like in this case. But on the other hand, if it's something simple enough, then I'm not going to give you a graph and only for you to populate the values of the edges and also the heuristics. So in this case, I give you an example. Um, but once again, even if I give you an example, you don't have to use it. Okay, there's nothing here that says you have to use this one. Wow, you can come up with your own. This is one that works, which means if you say I don't want to copy anything from tech, I want to come up with my own. You can try to use your time. Okay, that's a noble thing to do for homework assignments, but for a final exam, that might use up additional time that you may not be able to afford. So make M the start vertex, Q is the destination, and you need to determine the distances of the edges and the heuristic values. Okay, so do you guys want to work on this one? Okay, all right. All right, so let's go ahead and get a visual first. Okay, so we want to get a visual of what this graph is going to look like. So we got 4 vertices. We have M is the start, Q is the destination, and then we have P and R in between. So here's P and here's R. And the edges are M goes to P, there's one here. M goes to R, there's another one here. R goes to P, R goes to P, like that. And then P goes to Q, like that. Okay. So this is the structure of the graph. Now we have to find out, okay, how do we assign distance of the edges and also heuristic values so that one edge is going to be revisited, okay? So now the question is, which edge do you think is going to be revisited? That's the first thing. P to Q, exactly. So P to Q is the one that is going to be the one we are targeting and say that, oh, we're going to revisit that one. Okay, so we want to target PQ as the one to be revisited. So what kind of went through your mind when you say, okay, it's got to be PQ that we're trying to revisit?
You get there from M and then you get there from R going to P.
It's an overlap between two paths from the start vertex to the end vertex. Let me say that one more time. There are two paths from M to Q. You can say M, P, Q, right? That's one path. You can also go M, R, P, Q. That's the other path. The one edge that is overlapping between those two is PQ. So that means, we're trying to trick the A star algorithm to go for one of these paths first, only to realize, oh, that is not working. Okay? There's a shorter way to do it. Then it will revisit the other one, which means it has to re-explore PQ as an edge. Is that okay? All right, so now that we know PQ is going to be revisited, the cost of the edge or the distance of that edge really does not matter because it is the same edge from the perspective of the two potential paths from M to Q. So I'll just give it like 2, doesn't really matter. But the other ones are now kind of important because I need to somehow make sure that I can trick the algorithm to go for one path which is not the shortest one, and then it has to go back to go for the other one. Okay? So that means from M to P, the cost of this edge versus the length of the path from M to R, then to P, they have to be different. Because if they were the same, then we have two paths of identical length, and we know the A star algorithm is not going to revisit something just because they have equal length. Okay? It has to be less than. So they have to be different. The other thing is when we start with M, because M is the only element in O to begin with, it automatically puts P and R into the set O. We want to trick the algorithm to go like, oh, okay, let's just go for P first, because R doesn't look very attractive. Then we have to go back and go like, oh, I guess that wasn't really the shortest path. Then it has to go back and revisit, R. Are we still doing okay so far with this? Okay. All right. So let's see. I'm trying to run the algorithm in my head first to kind of make sure that the values would work. Hmm? Yep.
So like with so you pick the cost so that they don't match. Do you pick the more expensive cost to have like a cheaper looking heuristic?
Mm-hmm. Yep.
Okay.
Okay, so the first thing we kind of know is we want P to look really good. Okay, because when we get here, because we know that P and R will both of those will be in O after we pick M as C as a variable. So we want P to look particularly good, and the only way to make it look particularly good is to make the heuristic as low as possible. It's like, pick me, I'm really close to the destination. As opposed to R, we want to make this as realistic as possible. So whatever R has to be is going to be 2 plus the actual distance of the edge RP. Okay, so if we just randomly select a value here, let's pick this to be 3, then we want H of RQ to be as realistic as possible, which is the actual shortest path from R to Q, which is 5. So this is going to be 5, okay? But we also want, P, not MPQ not to be the shortest path. We want it to be actually the longer path. So that means when you look at the length of MPQ, it has to be greater than the length of MRQ. Are we doing okay so far with the analysis of how to reconstruct an example to make this work? Yes?
You say that your path M to P to Q has to be shorter.
Longer. Has to be longer. Has to be longer because we're trying to trick the algorithm to go that way first, only to realize, oh, this is too long.
Yeah, so in A star, it's actually gonna go to the longer path first, like from your
Right.
start vertex.
Mm-hmm. So are we still doing okay? Okay, so I'm just kind of putting a 1 here and then putting a 5 here and see whether that works. Okay. Because 1 MPQ has a total length of 7, and then this one has a total length of 6. Okay, but are we tricking it enough to go that route? Yes.
Wait, doesn't the A star algorithm, isn't it a greedy algorithm? So
It is greedy,
it'll look at every vertex.
but it's greedy based on the value of F,
Okay,
not
so
based
not
on
the value,
G.
whatever the next available
Yeah.
or close to.
So when it looks at, so P has an F value of just 5 because the heuristic from P to Q is 0. And then R has the more realistic version, which means it is 1 plus 5, it is 6. So it's going to pick P first. When it picks P, it has to look at all the outgoing edges of P, and its only outgoing edge is from P to Q, so it will explore Q. But since this is the first time we got to Q, that means it will update the G value of Q from infinity to 5 plus 2, which is 7. Okay, so that's the first time we visit Q using the edge PQ. Is that okay? Then we go back, we look at the set O, right? At which time there will be 2 elements left, which is Q and R. We pick the one that has the lower F value. The F value of Q is going to be exactly 7. And then the F value of R is going to be 1 plus 5, which is 6, which is lower than the F value of Q. Then we'll pick R, right? We pick R, we explore its outgoing edge, which is going from R to P. It has a value of 3. So now we are actually going to update the G value of P and put P back into the set because we just found a shorter path from the start vertex to P. The first one that we found was not good. The second one is better. Is that okay? So P is back onto O, and the next iteration is going to select between P and Q. The F value of P is going to be 4 plus 0, which is only 4. But the F value of Q is 5 plus 2, which is 7. So it's going to pick P to explore. Once it picks P, it will look at all the outgoing edges of P, and will find this outgoing edge. Then we'll figure out that G of Q can be 4 plus 2, which is 6. 6 it will be less than G of Q at the time, which is 7. Then it will trigger the algorithm to update the G value of Q, the F value of Q, and also the previous of Q, so that, but basically the point is the HPQ is used again. So this will definitely do the trick. So are we kind of doing okay so far with this example? There are several levels that I want to ask, whether you guys are understanding or not. The first one is, does everybody understand why this works? Why this is going to meet the requirement of the question of if you run the A star algorithm, the HPQ will be visited twice. So are we good with that one? Okay. The second level of the question, which is kind of like, if this is representing a graph with xy axes, the next question is, what is the derivative of the value of y? Okay, and that is, do you understand my reasoning of how I came up with these values? Which is a more important question, because you're almost guaranteed that you won't be asked the same kind of question here. So the most important point is, do you understand my reasoning? Do you understand how I came up with the values? Given the graph already, are we okay with that one? Sort of. Yep.
Can you explain it again?
Well, I just did.
No, between, I get from P to Q, but from M to P and the R, the first you said you weren't sure if it was going to work, and then you crafted the algorithm for it,
Right.
right? So, did you just make a informed guess, or what?
It was an informed guess, but then I ran the algorithm in my head to verify that it would work. Yep.
So like when you pick those values, did you just pick a path for one cost, pick another path that's cheaper, and then have the more expensive cost have the nicer looking heuristic, and the cheaper path have the worse looking heuristic, so it has the backtrack? Is that all?
Yes. So basically, you cannot reverse these two, by the way. You cannot make this one 4 and make these two add up to 5 and expect it to visit this edge twice. And the problem has to do with it has to choose between these two and choose this one first. Is that okay? And that's the bottom line. It has to choose between these two and make sure it chooses P first. Are we kind of doing okay? How many people can run the A star or the Dijkstra's algorithm in your head? Like, really? No? Okay, not yet. So that might be something that you want to shoot for, is to know the algorithm well enough that you can run it, not finding the exact values, but to find out, okay, how am I updating the values? Just be able to do it quickly, maybe not entirely in your head, but with like slight annotations on the graph itself, but you want to be able to do without doing a full trace. Yes?
When you go back up to the A-star algorithm in this test, and can you spot the place where you're looking for more costly path? Because that's how you're gonna go to P first from M.
Correct. So this is one thing you can do. Okay, what you guys can do is to finish up the heuristic values. Okay, because we already have P of H of PQ, we have H of RQ, and we just need H of MQ and and then H of QQ. Those two are irrelevant. Okay, you can use whatever legal value that you want. Okay, so let me just kind of write it down here. Do you really have a choice with this one? It has to be 0, right? Because it cannot overestimate. And it has to be non-negative either. Okay, so this has to be 0. Okay, fine. What about this one? This is the last heuristic value you have to come up with. But why is this one irrelevant? Because you don't have a choice. The heuristic value is only useful when it is used to compute an f value. And the relevance of the f value is when you have multiple things in the set O, you have to choose which one to use, right? When do we put M, which is the start vertex, into O? Before the loop, right? Before the loop started, it's during the initialization. Was it the only thing in O at the time? It's the only thing, which means I don't have anything to compete with M, which also means whatever the heuristic value of M is, it doesn't really matter because I'm going to choose M anyway. Is that okay? So you can choose, so the heuristic value from M to Q can range from 0 to the actual shortest path, which is 6. Pick any one of these values between 0 and 6, it will still work. It doesn't really matter. I mean, if you choose other values, it would actually work too, but we want to kind of play by the same rules of the heuristics not overestimating. So that's why the only valid range of values is from 0 to 6 inclusively.
So because we can't overestimate, we should make the heuristic for M and Q 7.
Correct. Yep. If you made it 7 in this case, the algorithm would still work because it's not going to be misinformed to choose another vertex when it's not supposed to. Because when you have M as a choice from O, it would be the only choice, which means it doesn't have to choose anything, which also means the F value of M is of no consequence to us at all. But that's only because it is a start vertex. Is that okay? So this is one thing that you guys can do if you want something to help you kind of get more practice with the algorithm. Copy this and do a trace on this one. Okay, now if you want to do a trace on this one, you can also do a trace on this one. In addition to A star, also use Dijkstra's algorithm, because now you can kind of compare side by side and go like, okay, if I run Dijkstra's algorithm, this is what is going to happen. If I run the A star algorithm, this is what's going to happen. So let me ask you now, okay, we can try to work on this really quickly in our head. Yep.
I wanted to ask, so if we wanted to come up with our own examples,
Mm-hmm.
or like our own graph to try and do the same thing on a different graph, would we just need more than one path and a bottleneck? Because it seems like it needs to like
Yep.
have both of those, right?
And also working with your H values accordingly, so that it would initially choose something that looks promising, but it's really not the best one. And the actual shortest path, everything is realistic, so it doesn't look attractive at the beginning. Yep. So that's the bottom line. But getting back to what you can do with this example is to run Dijkstra's algorithm on the same graph, okay, and then see how the two algorithms are different. So if you run Dijkstra's algorithm, do you think you will revisit any edge? Nope. Because with Dijkstra's algorithm, it starts with the destination. So if you start with the destination, there's only one shortest path from P to Q, which is just following that edge, right? Then it's going to look at the incoming edges of P, which is from M and R. Okay, so then it will find one path to M here. It will find one path from R here. Is that okay? And it would put M and R both into the set Q in Dijkstra's algorithm. So then we have to choose one to expand. At that time, R would be the one that is closer to the destination. So it would choose R from the set Q. And then R also has an incoming edge of M. And at that time, it will find that M has a shorter path. But it's not going to revisit an edge. It will revisit a node or vertex, but it does not revisit an edge. And that's Dijkstra's algorithm. You like Dijkstra's better. But A star makes it easier for me to make questions because there are more moving parts and more degrees of freedom. But it would be nice to run both algorithms and trace both, on a piece of paper, just so that you get more practice with, following those algorithms and understanding how they work. Okay, as you work more on the algorithms, you will start to understand how they work. Yep.
So it would never visit MTP and Dijkstra's algorithm.
Huh?
It would never visit MTP and Dijkstra's.
In it will visit an edge, because when P is removed from the set Q, we will put both. It will find this path as the shortest path at that time. It will also find this path at that time, but then it will put M and R both into Q, right?
But then it'll look at R first.
It will look at R first because R has a smaller L value at the time. Because R would have an L value of 5, M has a L value of 7 at the time. So it's going to choose R from Q, right? And look at all the incoming edges into R. There's only one incoming edge to R, which is from M to R, right? So it would then find that we have 1 plus 5 as an alternative to the current L value of 7. So it's going to update the L value of M the second time. The first time it updates is from infinity to 7, and then the second time it updates, it's going to be from 7 to 6, because it would have found the shorter path like that. But the best way to do it is really to run the algorithm, on a piece of paper, so that way, you get more practice with the algorithm itself. So are we good with question number 5? All right, very good. So with Prolog, okay, the kind of question I can ask in Prolog is going to work with something similar to the cousins program. It's not going to be exactly the same, but it will be something similar. I'll give you all the definitions, all the clauses, and all the rules, and then I'll ask you, okay, so if I were to ask this question, how is Prolog going to answer that question? Or I might ask you, okay, if I ask this question, the answer is true, what other clauses do we need to add to the program in order for that query to return true? So you will still kind of need to understand how Prolog works to the extent of what you need for your homework assignment to work. Because there are many other things about Prolog that we didn't talk about, okay? Like the cut operator, how to use a list, how to use a structure list, that sort of stuff. I'm not going to ask you those, okay? I'm only going to ask you about the concepts that you need in order for your homework assignment to work. And I'll give you the solution to that on Wednesday. I got mine to work already, so I can give you the solution on Friday. And I'll explain that too. So are we okay so far with the Prolog stuff? Yes? And I think I said that I would not ask questions on time complexity. So I'm going to keep my word and not to have any questions on time complexity, which doesn't mean it is not an important topic of this class. It just means that it is a little bit difficult to ask questions at a particular level, when it comes to time complexity. Yep.
How many nodes would you be putting on for Dijkstra or Eastar? 5.
I do not know yet. So I'm not going to make any guarantee of not more than so and so. It depends on the shape of the graph, right? I can give you a graph with 20 vertices and no edges. Which makes running either algorithm like, oh, we're done. Okay, so it depends on the complexity. I can give you 5 vertices where everything is fully connected, right? So there are vertices to connect from every vertex to every other vertex and backwards. And then give those things, values, So that can be a little bit, difficult to track down. But the algorithms, both algorithms, should be, especially Dijkstra's algorithm, should run through it pretty quickly because a lot of those edges are actually not going to be explored. Okay, any other questions? Before Wednesday, because I'm assuming that you guys would do some studying before Wednesday, um, the one thing about both Dijkstra's algorithm and the A star algorithm is really to understand why we have what each line is doing. Okay, why is it there? What it is doing, and how is it contributing to the algorithm as a whole? Okay, that really is a kind of important part because it's making all the pieces kind of connect together. It's like, oh, what is the significance of this conditional statement? What is the significance of the condition here? Why do we put n back into O? Okay, why do we update these things? Why do we initialize the values the way we do? Why do we choose if there are multiple elements in O? Why do we choose based on this criterion? Okay, so all of those are questions that you kind of want to ask yourself as you go through and try to understand the algorithm. It's not really just to mechanically go through and just perform the steps one by one, but to really understand the rationale behind the code. Because once you understand the rationale behind the code, it will become almost easy for you to run the algorithm in your head. The reason why you may not be able to do it now, to just kind of like look at the graph and kind of go through the algorithm in your head, is maybe it's because you're not understanding the meanings and why we are performing these operations. Because once you understand the why and how they all connect together, it would be easier for you to kind of run the algorithm in your head. So, any questions? If you know a scripting language, okay, like JavaScript or something like that, writing a program to actually implement the A star algorithm or Dijkstra's algorithm can be beneficial. Now, I understand it's not going to be something that you have to turn in, it's not going to count for any points, but as you write that program, as you test the program, as you create test cases for the program, you might gain insight of how the algorithm works. Because debugging is one of those kind of triggers that help people to understand how a particular program works. But whether it's time efficient or not is up to the individual. So I cannot say that it's going to work. I cannot say if you do it this way, you're guaranteed, a perfect grade for your final exam. Yes.
I was just curious, since there was two questions on here that were sort of unrelated, since the smoke last semester.
Right.
Do you maybe have the one from the previous semester?
That is already on Canvas. Yeah, so that one is already on Canvas, and we can go over that one on Wednesday. So let me just kind of point out where to find that one. So the one from spring 2018, which is 2 semesters ago, is already here, and I think it's this one. Let me just double check. Take a quick peek at it. Yep. So this is from last year, and this is without the smoke effect. So you can work on this one, and then we can talk about this one on Wednesday. So Wednesday is kind of like we can review the prologue program. We can review this particular sample test from 1 year ago, or any other topic that you guys want me to kind of go over. So it might be helpful to kind of review all the material before Wednesday, just so that you have an idea of, what kind of question you might want to ask on Wednesday. All right, so I'll see you guys on Wednesday, and have a nice day.